Giant students, welcome to my YouTube channel. Students, as your teacher, I promise you that I will always be in one of the three places. Now you must be wondering, which are the places I am talking about? Students, first place where I will be always with you is in front of you, to guide you, teach you, lead you by example and cheer you on. And the second place where I will be always with you is beside you, so that you will not walk alone and I can catch you should you stumble. And the third place where again you will always find me is behind you, to give you a gentle push in the right direction, knowing that I have got your back. So the essence is, students, teachers are always with you, whatever be the circumstances. Right, students? We are only concerned about the welfare of our students. Clear? Okay. With that, let's begin today's session. We are going to start a new topic, which is magnetism. And in this unit, we will first start with the intro. We will first start with the bar magnet, properties of a bar magnet. And before that, some history about the natural magnets and bar magnets. So students, historically, Thales of Miletus, he found that lodestone or magnetite, which is actually naturally occurring iron ore, it is found to attract small pieces of iron. And most importantly, these pieces of iron, when brought in contact or placed near this iron ore, is itself found to get magnetized. And also, when the lodestone is freely suspended, then it tends to align approximately along the geographical north-south direction. So this fact was used by the Chinese in navigational aid. So this is the reason why magnetite is also known as lodestone or leading stone. So this magnetite, which is the naturally occurring ore of iron, is actually known as natural magnets, right? So lodestone, it is magnetite. Actually, it is the ore of iron, and it is Fe2O3. So what I've stated is that Thales of Miletus, he was a Chinese, he found that this lodestone or magnetite, which is the naturally occurring ore of iron, that is Fe2O3, attracts small pieces of iron. And as I told you, these iron pieces, when brought in contact or placed near the lodestone, itself get magnetized. That we will discuss. It is known as induced magnetism. And these lodestone, when it is suspended freely, then it tends to align itself in a particular direction, that is along the geographical north-south. So this concept was used in the ancient times as navigational aid. For navigation purposes, this was used. So that is the reason why lodestone is also known as magnetite, or it is also known as leading stone. It is also known as leading stone. So these are the natural magnets. Lodestone, that is magnetite, which is naturally occurring ore of iron. Now students, there are some drawbacks of this natural magnets. Obviously, they have got low magnetization, and obviously they have got odd shapes. They don't have any regular shapes, isn't it? So due to their odd shapes and low magnetization, they can't be used for any practical purposes. So basically what you do is, we take a iron bar or iron rod or basically a soft iron of a particular shape, whichever shape we desire, and then we rub it with a natural magnet in a particular way so as to magnetize it. So after magnetization, that iron bar becomes a magnet, and that is when we call it as artificial magnet. Clear, students? So we normally make use of iron, steel, and for bar magnet we make use of Alnico, A-L-N-I-C-O, aluminium, nickel and cobalt. These are the three things which are used to make a bar magnet, which is made up of Alnico. Before we proceed further, before we start with other topics, related topics, I would like you to watch this short, very interesting video. This is about the different shapes of magnet, then the properties associated with the magnet, and obviously the uses of magnet. So here's the video. We will discuss the properties of magnet, and before that we will discuss the shapes of the magnet. This is, students, a horseshoe magnet. This is a bar magnet having one end as North Pole, the other one as South Pole. This is a magnet which is in the form of a magnetic compass and needle magnet. Now let's discuss some very important properties of magnet. First property is the attractive property. When a bar magnet is brought near a heap of iron fillings, they cling most near the two ends of the magnet, which are known as the poles of the magnet. The attraction is maximum at the poles. It may be pointed out that the poles are situated near the ends of the magnet and not exactly at the ends. In the case of horseshoe magnet, both the north and the south poles face each other. Hence, the attractive force get doubled. Now, the second important property is directive property. A magnet, when suspended freely, aligns itself approximately along the geographical north-south line, such that the north pole of the magnet is approximately towards the north of the earth and the south pole is towards the south of the earth. Third very important property is unlike poles attract while the like poles repel. If the south pole of a magnet is brought near the north pole of another magnet, they are found to attract each other. On the other hand, if the north pole of a magnet is brought near the north pole of another magnet, or south pole of a magnet is brought near the south pole of another magnet, they are found to repel each other. Therefore, unlike poles attract each other and like poles repel each other. Here, it should be mentioned that an isolated magnetic pole does not exist. That is, magnetic poles always exist in pairs. Next property is magnetic induction. It is also known as inductive property. When a piece of substance such as soft iron, steel, cobalt, nickel, etc. is placed near a bar magnet, it acquires magnetism. The magnetism so acquired is called induced magnetism, and induced magnetism is temporary. As the magnet is removed, it loses its magnetism. Now let's discuss about the magnetic field lines. The magnetic field line is the path along which an isolated north pole will tend to move if it is free to do so. The concept of magnetic field lines was developed to visualize the strength of magnetic field in different regions of the field. The regions where the magnetic field lines are close enough, that is crowded, the magnetic field is considered as quite strong there. Now let's discuss some few uses of magnet. Magnet can be used to make compass. It can also be used to make DC motor. DC motor is a device which converts electrical energy into mechanical energy. Magnets can also be used to make AC generator. Generator is a device which converts mechanical energy into electrical energy. This is the place where we can see the field magnet inside the motor. So students, what are the properties of the magnet which we have discussed in the video? First is attractive property. Now as we are aware, a magnet tends to attract small pieces of iron towards itself, and the attraction is maximum near the end points of the magnet, and those preferred region where the magnetic force of attraction is maximum are known as the poles of a magnet, North Pole and South Pole. So that is basically the attractive property. Second property which we have discussed is directional or directive property. Now this I have already told you, in ancient times this property of the magnet was used for navigational purposes, right? So if you suspend a magnet freely, then it will tend to align itself along the geographical north-south, approximately. Clear, students? So this property of the magnet of aligning itself along the geographical north-south, that is known as the directional or directive property. Third one, like poles we are aware repel each other, while unlike poles attract each other. This also we have discussed. And fourth, inductive property. When a small piece of iron is kept near a magnet, then the iron piece will itself get magnetized. This is known as induced magnetism. And the point to be noted is that induced magnetism is temporary. So when the magnet is taken away, then that piece of iron will lose magnetism. So that's induced magnetism. So these are the properties which we have already discussed in the video. There are some other interesting properties as well, like magnetic monopole do not exist. Now mono means single. So basically single magnetic pole do not exist. Magnetic pole always exists in equal and opposite pairs. Magnetic poles always exist in equal and opposite pairs. So this is a very, very important property of a magnet. So basically what I mean to say is that if a magnet is broken into several pieces, then each piece of the original magnet will have two poles, north and south. Both will be of equal strength but opposite nature. I will elaborate this with the help of this diagram. Suppose this is a bar magnet over here. This is the north pole and this is the south pole. And as you are aware, students, north and south, these are the two poles, and they are not exactly the end points of the bar magnet. They are near the end points, and these are the preferred regions near the ends of a bar magnet where the magnetic force of attraction is maximum, right? So suppose this is the original bar magnet. Now it is broken into various pieces like this. It is suppose broken into various pieces. suppose magnet is broken into these 4 pieces. Then each piece will have north pole and south pole like this. And in each piece, the north and south pole both will be of equal strength and obviously are of opposite nature, right? So single pole do not exist. Magnetic poles always exist in equal and opposite pairs. Whatever small be the size of each piece, every piece of the magnet will possess 2 equal and opposite poles. Equal and opposite means poles having equal strength but different nature, opposite nature. So this was very interesting and important property. Magnetic monopole do not exist. Poles, that is north and south pole, always exist in pairs, right? And students, there is another important property. Repulsion is the surest test to distinguish between a magnet and an iron bar. Repulsion is the surest test to distinguish between a magnet and an iron bar. Now I will explain this statement. Suppose these are the 2 substances given to you. Both are identical, are of same dimensions, and their physical appearance is also identical. One of them is a bar magnet, the other one is a simple iron bar, right? We need to distinguish between the bar magnet and the iron bar. So how to do it? Suppose this is the iron bar and this is the bar magnet. Now students, look, it's a very simple logic. If this is a magnet, it must possess 2 equal and opposite poles. Suppose this end is the north pole and this end is the south pole. And in case of iron bar, it won't have any magnetic poles, isn't it? So now what happens is, if a third magnet is brought near this one, then one end of the substance will get repelled while the other end of the substance under consideration will get attracted. Understood? While on the other hand, if this magnet is brought close to the iron bar, then both the ends of the iron bar will get attracted to the magnet. So if one end of the substance, any of the 2 substances, if one end get repelled from the magnet by placing closer to it, then it means that that substance under consideration but must be a magnet. And if it happens that both the ends get attracted towards this magnet, then it must be an iron bar. So that is the reason why repulsion is said to be the surest test to distinguish or differentiate between a bar magnet and an iron bar. I hope you have understood this concept, students, right? So this is based on the concept that like poles will repel each other while unlike poles will attract each other. And this being an iron bar, both its ends will get attracted towards it because it do not have any poles. It is unmagnetized, right? Okay, students. So these are the properties of a magnet which we have already discussed in the video, as well as we have recapped the entire thing, right? Now let's discuss the magnetic field lines and its properties. So basically, students, magnetic field lines, it is also known as simply the field lines. It is actually a hypothetical concept. Magnetic field lines actually can be defined as the imaginary path along which an isolated imaginary north pole would move if it is free to do so. But from junior class point of view, you can just remember that it is a hypothetical concept. Hypothetical means imaginary concept. It's not real. So, magnetic field lines. Let's discuss this topic. Magnetic field lines. So, first point to be noted is that it is a hypothetical concept. Hypothetical means imaginary concept. It does not exist in real. So you must be asking to yourself, what's the purpose of developing this concept? So the answer lies in the fact that the concept of magnetic field lines has been developed so as to visualize the strength of magnetic field in a given region. In a given region, in which part of the region the magnetic field is stronger, in which part of the region the magnetic field is weaker, so that we can visualize by drawing the magnetic field lines with the help of magnetic compass needle and a bar magnet, right? So basically magnetic field lines, this concept has been developed. The concept has been developed so as to visualize the strength of the magnetic field in a region. The strength of magnetic field in a region. So that is why this concept of magnetic field lines is developed, right? Now let us discuss some of its properties. In the video, students, you must have watched the magnetic field lines, how the magnetic field lines can be visualized, isn't it? So I will draw that diagram. Suppose this is the bar magnet. Again, I must remind you of the fact that magnetic poles always exist in equal and opposite pairs. So if this is a magnet, it must have two equal and opposite poles. One is the north pole, the other one is the south pole. North, south, they have got some pole strength. Both are of equal magnitude but different nature, isn't it? And these poles are not exactly the endpoints, but near the endpoints of the magnet, where the magnetic force of attraction is maximum. So it is somewhere in this region, near the endpoints. So suppose this is the north pole, and let us consider this to be the south pole. Right? So if you want to plot the magnetic field lines, then students always remember the magnetic field lines are always in the form of continuous closed loops. They are in the form of continuous closed loops. They neither have any starting, that is emanating or initiating point, nor do they have any terminating or end point. So I will write the properties as well, right? So first property is magnetic field lines are in the form of continuous closed loops. They are in the form of continuous closed loops. So this is it. Inside the body of the magnet, the field lines are directed from south to north, like this. The field lines are directed from south to north. While outside the body of the magnet, students, the field lines are directed from north to south, like this. It is directed from north to south. You need to indicate this arrow. So this becomes a closed loop. So this is what I am talking about. Magnetic field lines are in the form of continuous closed loops. And you need to remember the direction. Inside the body of the magnet, the field lines are directed from south to north. And outside the body of the magnet, the field lines are directed from north to south. So you can complete this diagram. It should be like this. Let me draw a few magnetic field lines for you. So inside it is from south to north, and outside it will be from north to south. I am not completing it. but it's the fact that it is in the form of continuous closed loops. It's like this. So inside the body of the magnet, the field lines are directed from south to north. They are directed from south to north, while outside it is directed from north to south. So diagram should be like this. Try to draw symmetrical diagram. Okay, these are the magnetic field lines. You can continue over here as well, right? You can complete it. So this will give you a visual representation of the magnetic field line. So that's the first property. Magnetic field lines are always in the form of continuous closed loops. It is in the form of continuous closed loops. So they neither have any starting point nor do they have any terminating or end point. Second, inside the body of the magnet, the field lines are directed from as I told you, from south to north, while outside the body of the magnet it is directed from north to south. It is only then it will be in the form of closed loop. Clear, students? Third, these are some of the properties of field lines. Now, what will be the direction of the magnetic field at a point? Now look, it's a curve, isn't it? It's a curve. So if you want to find out the direction of the magnetic field, say at this point, then what we'll do is, the field line is along this direction. So at this point we'll draw a tangent. So it will be like this. So this will be the direction of the magnetic field at point A. So suppose magnetic field is represented by capital letter B. This is B. B stands for magnetic field. This is magnetic field, suppose. So the magnetic field at a point is given by drawing a tangent at that particular point. Clear? Suppose you want to find out the direction of the magnetic field at this point, say at point C. Then the magnetic field lines at point C is along this direction, like this. So at point C, you will draw a tangent. Tangent is like this. This will be the direction of the magnetic field. Clear? At this point, students, the direction of the magnetic field, again, it is like this. So at this point, you will draw a tangent like this. So third, very important property is, the direction of the magnetic field at a point is given by drawing a tangent at that particular point, right? So the direction of magnetic field is given by drawing a tangent at that particular point. So this was regarding the direction of the magnetic field in the region of the bar magnet, right? Fourth property. Now look, students, as I told you, the concept of magnetic field lines has been developed so as to visualize the strength of the magnetic field in a given region. So here it's pretty clear. These are the regions where the magnetic field lines are crowded. They are closer towards each other. So here the magnetic field strength is stronger. While in this region, the magnetic field lines, they are less crowded. So there the magnetic field strength is weaker, right? So basically the relative closeness of the field lines, the relative closeness of the magnetic field lines gives a measure of the strength of the magnetic field. So the relative closeness of field lines gives an estimate of strength of magnetic field. Clear, students? So I must again repeat, in the region of magnetic field, the portion at which the field lines are crowded, there the magnetic field must be stronger. While on the other hand, in the region where the magnetic field lines are less crowded, there the magnetic field strength must be weaker. So basically, the relative closeness of the field lines that gives an estimate of the strength of the magnetic field in that particular region. And students, another very important property is no two magnetic field lines can ever intersect with each other. What I mean to say is that magnetic field lines can never intersect each other. Can you think of the reason why the magnetic field lines cannot intersect each other? It is because, students, the direction of the magnetic field at a point is unique due to a source. The strength of the magnetic field as well as the direction of the magnetic field at a point must be unique. Unique means a single particular direction, right? So at any given point, magnetic field should have a single particular direction. And also, in this point we have discussed, the direction of the magnetic field at a point is given by drawing a tangent at that particular point. So, why two magnetic field lines can never intersect each other? I will elaborate this with the help of a diagram. Let us consider this particular diagram, students. Okay. This is one of the magnetic field line. Suppose this is the first magnetic field line. Correct? Let's consider two magnetic field lines are intersecting at a particular point. Let's see what happens then. So this is the first magnetic field line, and suppose this is the second magnetic field line. This is the second magnetic field line, and this is the point of intersection. Suppose O is the point of intersection. Again I repeat, students. Let us consider the two magnetic field lines intersect at point O. Now at point O, if you consider the first field line, then the direction of the magnetic field at point O due to the first field line will be given by drawing a tangent at this particular point. This is suppose the magnetic field B1 at point O due to first magnetic field line, right? Now at the same point O, the direction of the magnetic field due to the magnetic field line second would be given by drawing a tangent to the second field line. It is B2. Now look, students, what is happening is at the same point O, we have got two different directions of magnetic field, which obviously is not feasible, which obviously is not possible. This is the reason why magnetic field lines can never intersect each other. I repeat, students, the direction of the magnetic field at a point must be unique, must be particular, must be in a single direction, isn't it? Here what is happening is, if we assume the field lines to be intersecting with each other, then at the point of intersection we are getting two different directions of magnetic field. Whereas at point O there should be only a particular direction of magnetic field, but here due to the intersection of magnetic field lines we are getting two different directions of magnetic field, which is obviously not possible. So this is the reason why magnetic field lines can never intersect each other. So students, these were some of the properties of magnetic field lines, right? So I hope you have enjoyed thoroughly this particular session, and this was just an intro regarding the magnets, the properties of magnet and field lines and its properties. So that's it for this particular session. Do join me in my next lecture then. Till then, do take very good care of yourself. Always be happy. Thank you.